In this video, we're going to look at constant pressure applications for closed systems, and we're going to look at the specific case in which we have no other work except the movement of the piston. If heat is added or heat is taken away, and the piston's going to move, there's going to be boundary work done there, but otherwise, there's going to be no other work. So it's going to be this specific case. And also, recall uh, in this specific case, if there's just this boundary work of the piston moving without any additional work, it's going to be P delta V is going to be the boundary work. And also, we can assume there's no change in kinetic energy since there's no flow of any gas, no change in elevation. So that's going to be zero. So we're going to have something like this. And now we can bring this P delta V to the other side of the equation. Remember, P is constant. That's why we could say P delta V rather than say delta PV. We were able to kind of take the P out and plus this. And recall that this is the change in enthalpy, like this. Again, that's only going to be true. We can use this equation here, which again comes down to Q equals delta H. And we can only do that in the case there's no other work, there's just this piston, constant pressure, and we can use this. We're going to look at a couple of problems using this. So let's take a look at this problem. A piston cylinder assembly contains 0.5 kilograms of saturated vapor at 150 degrees C. The weight keeps the vapor at constant pressure so that, if any heat is added or taken away, the piston would go up and down and keep the pressure constant. Heat is removed until the water vapor becomes a saturated liquid. How much heat has been removed? So we'll take a look at this problem. So we have a situation like this. Again, we have constant pressure here. We have saturated vapor, and we want to, we have heat being removed. So if you wanted to, you could even put a little view like this out here. And so we'll be going along one of these constant pressure lines. We're not sure which one on our TV diagram, uh, but we'll be starting as a saturated vapor. That means we're going to start over here somewhere. And heat is being removed, again, at constant pressure because of the piston. Heat is being removed until we end up with a saturated liquid like this. Now, we don't know what pressure yet. We're going to find that out in a minute here. And the thing to remember is that there's no other work. So constant pressure. No other work except that boundary work of this piston at constant pressure. So that means we can use the equation we just looked at, which was Q equals a change in enthalpy, like this. Now we'll look at our two states. We have a saturated vapor to start with. Again, it's over here. Let me write this, say state one. And we know that state 2 is a saturated liquid. And so we're going to have to find out what we have here. So we can look up in our table in the saturated steam water table. We can look up 150 degrees C. Now in my table, that's table A10. You may have a different table depending on what book you're using. So 150 degrees is this right here. And we know we're going to need the enthalpy because we need to know the change in enthalpy. And that's actually maybe the only thing we're going to need in this case. So let's go across and look across the row. 150 degrees. So we're starting out as a saturated vapor. So that's going to be this value over here under Hg. So it'd be 2746.5. So again, we're at 150 degrees C, by the way. And also, we might as well write down our saturation pressure. That was 0.4758 MPa. So that would be what, like 475.8 kPa. Like this, we may not need that, but we'll write it down. And what did I say for the saturated? Then at 150, we have Hg was 2746.5. And that's going to be kilojoules per kilogram. And we know, again, we're at constant pressure, which was 475.8 kPa. I'll just put it on. It'd just be helpful to see it here. And then we're going to have a saturated liquid at the end. Now, obviously, our pressure is going to stay the same. So we want to find uh, what's going to happen at state 2. So we're going to have the same pressure at state 2. And actually, if you look at how we've drawn this here, notice the temperature will also be the same because notice it's a horizontal line here. So we can use that same row that we used. So we're at 150 degrees C, and we're going to this time use H of F because we know we're a saturated liquid, and that's 632.2. Again, I'll just put the same values down up here. Like this. And believe it or not, I think that's all we're going to need. Because now we can apply our equation up here. Q equals delta H. And Q is equal, again, that's going to be H2 minus H1. And when we take that difference, this is negative 211, 4.3 kilojoules per kilogram. And then to find the actual heat transfer, how much heat loss we had, we'll multiply this by the mass. And when we do that, we get negative 1057.15 kilojoules. And the negative indicates that it's heat transferred out. Let's take a look at this problem. A piston cylinder assembly contains 0.25 pounds of steam at 400 degrees F and 80 psi. The weight keeps the vapor at a constant pressure. A total of 150 BTUs of heat is removed. What is the final state of the substance? Give the final quality. So we'll take a look at this. So once again, we have a constant pressure, no additional work. And again, we're removing 150 BTUs. So again, constant pressure. And there's no work besides, just the work of that piston moving up and down, and that's only caused by the heat being removed. And so, again, with no other work, we can use the equation Q equals delta H. So we'll keep that in mind. Now, the fact that we're given both the pressure and the temperature, that means it's very likely that we're going to have a superheated steam, but we have to check just to be sure. So if we look in our tables, first you can check 80 psi and see what the saturation temperature temperature is. So if we look up 80 psi on our table, in my table it's B11. Our saturation temperature you can see is 312.07, but we are at 400 degrees F, so that means it's superheated. And we'll look up in our superheated table. Again, in my book, that is table B12. And we look up 80 psi and 400 degrees. And of course, we're looking for the difference in enthalpy. So we have to find the enthalpy, and that's this column right here. And this is giving us 1230.6. But let me just show you that up here, that column is enthalpy. And so again, if we read 80 psi and 400 degrees, get 1230.6. Again, that's BTUs per pound mass. Let's think. I don't think we need anything else. So we're going to then go to state two. And what do we know about state two? We know that the pressure remains constant. So we know that P2 is going to be equal to P1, which is 80 psi. We, again, we can't find H2. So we're going to have to go ahead and apply our equation right now. So again, to apply our equation, let's apply that down here. We have Q equals delta H. But again, we don't have enough information to find H2 over here, but we can use our heat transfer rate to calculate it over here. Now, first of all, we should note that we're given the mass here, so we're going to have to use little q in our equation. So let me calculate. Little q is going to be the 150 BTUs divided by 0.25 pounds. And that's going to give us, would be that like multiplying by 4, I guess, huh? And so that's going to give us 600 BTUs per pound mass. And actually, since it's heat transferred outward, I'm going to put a negative in front of it up here, like this. So now we can start substituting into our equation down here. H2 minus H1, and this is our H1. Like this. Then we'll bring this to the other side, and looks like that's going to leave us with H2 being equal to what? 630.6 BTUs per pound mass. This. So now where do we go from here? So we know that in state two, then over here, that we have this pressure and this enthalpy. So we're going to have to look at our charts here and see if this is superheated or if it's a mixture or if it's saturated vapor, saturated liquid. Let's take a look. Again, go under your pressure. So again, in my chart, it's chart B11. We'll look under 80 psi, and we'll see what the range is for enthalpy. And for enthalpy, HF is 282, HG is 1183. So this falls right in between there. So so when we put this, let me just note this together with our pressure here, after looking at our table, indicates it's a saturated mixture. From table, was that B11 we found it's a saturated mixture. And then go ahead and calculate X. And actually, again, if you want to get an idea where you're at, remember we have constant pressure, so we're going to go like along these constant pressure lines. And we're at 80 psi here. And again, remember, we started up here at superheated, so we were maybe up here somewhere at state one, we're superheated. And then now we know that we're somewhere in here for state two, not sure yet exactly, but we know we're somewhere inside that region. And so if we calculate our H2 minus our HF divided by our Hg minus HF is going to be, again, these are all have the same units, so I'm going to not write down the actual units here. Now, you can, in the denominator, you can take the 1183.6 minus the 282, which is the Hg minus HF. But remember, of course, in these tables, it has it calculated for you that difference there here. The Hg and HF were given. I could just calculate the difference of those two, but it's given to us right here, the HFG, which is 901.4, like this. And let's put that in our calculator. I got approximately 386, like that. So that's the final quality. And so if you want to estimate it on here, so it's going to be about, 38% across, 38% from the left. So maybe estimated to be state two to be maybe like right here. So the final state would be a saturated mixture, and the final quality is 0.386.